All right, today we're going to talk about the voltage controlled low pass filter, aka VCF. So it shows up here. So the art of that thingy is this guy, this op amp, which we are going to use as a active low pass filter. And the voltage control part is controlled here by this JFET. This JFET that connects here. We are going to go back into this in more details later. So first we're going to look at the active low pass filter only. We are not going to talk about this bit here yet. So the input, which is either the ramp, wave, the square, or the white noise. So that gets mixed here, and that goes straight into the inverting input of the op amp. The positive is just grounded. Here I say ground, but in reality it's a virtual ground, because in the schematics the virtual ground is actually 4.5 volts. So half the supply voltage, so be careful about that. In my case, I'm going to consider it a true ground. So it changes things a little bit, but I think it's easier to understand. And okay, so the idea of using an op amp as an active low-pass filter is you basically attenuate any signal whose frequency is larger than the cutoff frequency. So that's why it's using a so here you can see the feedback loop, and the feedback loop has one branch with a very large resistor, and the other branch, it's hard to see here, but it's basically a T with two capacitors. So there's one capacitor here and there's another capacitor there, and the vertical branch of the T is actually this one, this spot going to the ground. I think it's easier to talk about it if we go straight to the LTSpice simulation. Okay, so this is my LTSpice simulation of the active low-pass filter part. So you recognize the op amp here, and this is the input going into the inverting input of the op amp. So here my V-in is not a ramp or a square wave, it's actually a sine wave, which is here. But other than that, I use the same setup. I use that same resistor, the same capacitor, and the same current limiting resistor, which is very high. So basically your V-in, so here I have it with an amplitude of 0.3 volt, but when it comes into the inverting input of the op amp, it is very, very attenuated. And here you can see the feedback loop. So the feedback loop has this guy. And what this does is to make sure that the feedback branch as a whole doesn't have too much impedance or too much resistance. Otherwise, you will have no control over the amplification, and it's probably going to go into saturation. So this is to limit the gain, basically, in case this branch has infinite impedance. Because as you know, if you have infinite impedance in the feedback branch, the gain is going to be very, very, very large, like 10,000, 100,000. So it can go to saturation very quickly. Okay, so let's try to explain what happens here. The gain of an op amp, when you have a feedback loop, and when the input is connected to the inverting input, the gain is equal to the resistance or the impedance in the feedback loop over the resistance on the input. So what happens is that the higher the resistance in the feedback loop, the more gain you're going to get. And the lower the resistance, the less gain you're going to have. So in case of a low-pass filter, what you want is that for frequencies that are relatively high or frequencies that are higher than the cutoff frequency, you want the gain to be low. And for that to happen, the impedance in the feedback loop should be low as well. So you want the gain to be low, and for that to happen, the resistance or the impedance in the feedback loop should be low. If the resistance in the feedback loop is high, then the gain is high. Okay, so that's the whole idea about this active low-pass filter in this particular configuration. To have a low-pass filter, so either you put a passive low-pass filter here, or you put a high-pass filter in the feedback loop, and this is what's happening here. Here you have a high-pass filter with those two caps and the resistor here. And why does that work? Because when you have a high-pass filter in the feedback loop, when the frequency is high, or more exactly higher than the cutoff frequency, the impedance is going to be pretty low. And that means that the gain is going to be low as well, which is exactly what you want. So for frequencies lower than the cutoff frequency, you're going to have a high gain. And for frequencies that are above the cutoff frequency, you're going to have low gain, actually unity gain, or even less than that. So that's the whole idea. Okay, so let's run this thing. So for now, so I'm using a parameter for to simulate the potentiometer here, which is the cutoff frequency pot. R29, which is the resonance frequency, the resonance potentiometer, I'm just gonna kind of ignore. All it does is changes the Q. So you can just ignore that for now. And let's run this thing and do a frequency analysis. Okay, so let's run it. Okay, so here you can see the typical behavior of a low-pass filter. So here you actually have a attenuation minus 10 dB here in the low frequency region. It's mainly because of that R33. So here you can see this is where the cutoff frequency is. So it's about 320 Hertz. And then you have the drop. What happens if you change the cutoff frequency potentiometer? Okay, let's try that. So let's change this guy and let's make it lower. So instead of 50K, we're gonna put 10K. What happens? Let's rerun. Okay, so it's moving the cutoff frequency. So now it's 710. It's moving it to the right. The lower the value for that resistor, the higher the cutoff frequency is gonna be. Okay, so now, so this is the same circuit as before. The only thing that changed is that I added the voltage control part, and I simplified it quite a bit. So here's the JFET, so it's an N-channel JFET, and it's basically used as a variable resistor, a voltage control resistor. So it's kind of doing the same thing as this one. Basically, by changing the V gate, so the voltage at the gate, you can change the resistance of the drain source channel. So this is the drain, this is the source, this is the gate. So by changing V gate, you change the resistance here, which is exactly the same as turning the pot there. So V gate, as you know, and here the source is grounded. And this is a true ground, as opposed to what's in the schematics of the book. As you know, VGS, or VG in my case, VG is supposed to be negative. It cannot be positive in theory. And the higher V gate is, so the closer to 0, the lower or the smaller the resistance in this path. In order to simulate the voltage control part of the whole thing, so you can basically put a sine wave on V gate. So it's kind of simulating an LFO. And so it's a sine wave that's centered at a -2 volts and with an amplitude of 0.1. So it goes from -2.1 to -1.9. So this means that the cutoff frequency is gonna change based on this voltage here. So that's why it's called a voltage control low pass filter. So if you run this thing, let's look at the input. And again, this input is very, very attenuated before it even reaches the filter, which may or may not be a good thing. I'm not sure. But that's the way it's done in the book. So this is the input and this is the output. And you can see that it's modulated. I mean, somehow it's modulated, at least in this zone. I'm not sure what's happening here, because here there's no modulation, but it's definitely modulated here. Okay, so I think I'm going to stop here, and the next video I'm going to make is going to be the voltage control amplifier, and then that's going to be it, I think. Bye.